what exactly is a moment of inertia? If you could explain that.
Yes. So we're gonna do a real quick linear to angular version, and what it's gonna do is it's gonna make you understand it in the simplest way I think possible. Remember, we have all of these linear terms that we learned. So the linear terms were mass, position, velocity, acceleration. Then we learned momentum, and force. To convert from linear to angular, we convert. We know that S equals theta times R, which comes from the equation for circumference, and we're actually going to use that to solve for most of these. So what you get is you convert using that equation to get theta, which is the angular displacement. So it's the rotational version of displacement. You get angular velocity, which is the rotational version of velocity. I'm writing it wrong, my bad. Velocity equals WR. And then you get alpha, which is the angular version of acceleration, okay? Which I was telling you earlier, comes from tangential acceleration. So technically, I should put the normal over here as well.
Yeah.
And then you have AN, which actually stays as normal acceleration, but it gets rewritten as W squared times R. Momentum, it's not based on these equations. Those three equations are based on geometry. The momentum equation is actually based on the right-hand rule, which is to say that momentum equals arm cross. I'm sorry, not arm cross. You just have to know it. It automatically converts to angular momentum, which is arm cross mv, which can be rewritten as IW, which is super convenient for rigid bodies. And then force becomes moment, which will be written as R cross mass times acceleration. All right, which would be written as I alpha. So take a look at what we just did here. We have the rigid body rendition. We have the rigid body rendition right here. And then we have the particle rendition, and I'll put it in blue, right here. But what happens is, look at the variables in themselves. We have, let me erase that. W, put it in red. I need the highlighter. We have arm, which is absolutely necessary to create rotation. You need the arm and a multiplier by the arm to create the rotation. So forget the arm. Arm and mass times velocity gives you momentum, right? Angular momentum. So momentum is based on velocity. And then force is based on acceleration. So if you think like this, if you look at the traditionals, you have velocity and acceleration are both being wrapped. If you multiply mass times velocity, you get one term. If you multiply mass times acceleration, you get another term. It's almost natural to think that you should be able to multiply mass times position to get a term that we've never seen before. Does it make some sense?
Mm-hmm.
That is what the moment of inertia is. The moment of inertia is a representation of angular position, but with mass. Does that make some sense?
Yeah. Basically.
So it's like it's abstract like that. It's a representation, and so I'll call it I. And I is actually equal to, oh my God, it's like it's called the second moment of inertia. And what you have to do is you have to take the integral, and it's like R cross mass times like position, but position's like squared or something like that. Please don't quote me on that. I do not remember it. I think that moment of inertia is the hardest thing for me in dynamics. I just know what it is, and because of that, I know how to use it. But like solving for it is always the hardest thing. But basically, what it is it becomes a representation of the angular version of mass. Okay? I always call it angular mass for this class. For this class, for every class, you have to come up with a very specific way of defining things. And it doesn't translate all the time. So for example, in this class it's angular mass, but in another class, you don't really need to look at it as angular mass. You need to look at it as something else. But what do I mean by angular mass? If you use F equals ma, you think of mass becomes the resistance to acceleration. It's like a resistance term. So if you think of like V equals IR, then this will be resistance to current. When you convert that, if you kind of do a direct parallel, when you do F equals ma, mass becomes resistance to linear acceleration. Does that make some sense?
Mm-hmm.
And so when I'm doing dynamics, I don't call mass the amount of matter. I don't care that mass is the amount of matter when I'm doing dynamics. I care that mass acts as a resistor to acceleration in dynamics. That's its purpose. So yes, the definition of mass is how much matter there is in something. But when I'm doing dynamics, the definition of mass is resistance to acceleration. That's the best way to understand it so that we can do the problems. Does that make some sense?
Yep.
Great. So what happens is when you now create the parallel equation, moment of inertia equals I alpha, you see it a lot more clearly. Everything becomes a parallel. So I becomes resistance to rotational acceleration. Does that make some sense?
Yeah.
And so that's the best way I can put it. That's why I call it angular mass. Because if this is mass in this version, this has to represent the angular version of mass because of its job. Okay?
Okay.
That's where it comes from. So that's the best way. That's the way that I always try to explain angular moment of inertia. It's the angular version of mass, which means that it represents how hard it is to spin something. It's the resistance to you spinning it. That's the best way for me to describe it without losing scope of how we're going to use it in the class, because that's how you have to think of it when we're doing this class.
Okay.
Cool?
Yep.
Cool. I always thought it was interesting though, because when you look at the proof comes from this whole, oh my God. The proof comes from this whole idea is that the proof comes from the idea that it's based on factoring a position, but conceptually it actually doesn't really have too much to do with that. So, but it is what it is. That's just one of the, I just think that's the trickiest part of dynamics. But once you understand that, we can keep on riding. We ready to keep doing the problem?
Yep.
Dope. So now we just set up our situation. And obviously, something that we didn't talk about, if it's based on the position of each particle, then that means that it takes not only the mass of the object, but the geometry of the object in account as well. So it looks at mass and shape. Mass
And shape.
and shape. And so what happens is if your object becomes a different shape, the angular, the moment of inertia changes. Okay, and so that's why you have all of the basic shapes and the moments of inertia that are associated with them. So if you know the basic shapes that create the object, you don't have to do the integral every time. You can just use a summation of the objects and make life easy for yourself. But what happens is in this problem, we have a wheel, and this wheel is unbalanced. Right? This wheel has some mass on the outside, some mass on the inside, and some mass like that. That's where the mass is. So there are huge void spaces where there isn't mass. I'm not going to go and find a fourth of a disk and cut them out. Instead of doing that, we use what's called the radius of gyration, this guy right here, to solve for the I in a different way. And I